Hello everyone, I'm Mrs. Williams. It's a beautiful day, and today we're going to learn some strategies to find the height of tall objects. I'm here at home, and yesterday we just ate our last orange, but as you can see behind me, we have our very own orange tree. And so take a moment and look at our orange tree. What are some things you notice about the oranges we want to pick? Well, when I look at my tree, I can see that all of the lowest oranges are gone. There's still a lot of oranges on the tree, but they're all in the upper half. And so I'm wondering, how high is that lowest orange? And then look at the oranges at the top. Those seem pretty high, and I wonder if I even have a chance of getting them. And so it'd be good to know how tall that tree is. So let's come up with a plan of figuring out what tools we need to pick as many oranges as we can. And so I'm going to show you two strategies to find the height of those oranges. One strategy uses the sun and shadows, and the second strategy uses a tool called a clinometer that helps us measure the elevation of objects. So let's get started. Okay, the sun is shining. Let's look at our first strategy using the sun and shadows. In order to do this, I need a little helper. So I asked my daughter, Morgan, she's home from college, to be my little helper. So honey, go out there and stand, and let's look at the shadows formed by both Morgan and the orange tree. So as you can see, as the sun shines and hits the back of Morgan and the back of the orange tree, a shadow is formed on the lawn. And what we could do is we can easily measure Morgan's height, or I'm sure she knows how tall she is, and then measure her shadow, and then measure the shadow from the base of the tree to the shadow formed by the highest branch. And then we can use ratios and proportions to figure out how tall the tree is. And if you look at the highest orange, it looks about a foot below the highest branch. And so we could just subtract 1 foot off whatever height we calculate, and then we know how tall that highest orange is, and then we could see what tools we have to try and get it. Okay, so I grabbed my tools. I have pencil and paper to record my measurements. I have a measuring tape. I'm going to measure in centimeters because it's a little bit easier to work with than inches and feet, because I'd have to do some conversions because things aren't always exactly in feet. So let's see what we've got. Okay, so I can see it's right here, 148 centimeters. Okay. Okay, we have the lengths of our shadows. I'm going to ask Morgan her height, figure it out, and let's look at how we can use mathematics to figure out the height of that tree. Let's take a look at our first strategy using heights and shadows. So if you recall, we have our orange tree, and our goal is to figure out the height of that orange tree. And so we had my daughter go stand in the lawn while the sun's rays were shining down on both her and the tree. And so as these rays were shining down, it caused the tree to form a shadow and my daughter to form a shadow.
And what we end up having is a situation with two similar right triangles. So let me draw out each right triangle. Okay, so the question is, first of all, how do we know that these are right triangles? Well, the tree, we can assume, is growing perpendicular to the ground, forming a right angle with the ground. And my daughter is standing straight and tall, and so she's also forming a right angle with the ground. We know the two right triangles are similar because the sun is shining down on both the tree and my daughter at the same time, forming the same angle with the ground. And so we know that they share these two angles in common. And since we know that the three angles of a triangle add up to 180 degrees, if we know these two numbers, it's going to determine this third angle measure. And so we know that the two triangles share three congruent angles. So the two triangles are similar. And so how does this help us? Well, the nice thing about similar triangles is that their sides are proportional. Well, what does that mean? Well, remember, we wanted to figure out the height of the tree using my daughter's height. And the sun's rays were helping us by creating shadows. So the tree had a shadow and my daughter had a shadow. When we have two triangles that are similar, or two figures that are similar, ratios of corresponding sides are equal. So that means I could create two ratios, set them equal to each other, and then I have an equation I can work with. So I can compare the height of the tree to my daughter's height with the shadow of the tree to the length of my daughter's shadow, or doesn't matter how we compare the side lengths as long as we are matching corresponding sides. So another way I could do it is I could create a ratio of the height of the tree and the shadow of the tree and set that equal to my daughter's height, the ratio of my daughter's height to the length of her shadow. So now we have two equations that we could work with. We can just pick one of them. And so the question is, which of these would be our unknown, and which of these values do we know? Well, we know that we don't know the height of the tree, but we did take some measurements. We saw that the length of my daughter's shadow was 148 centimeters, which is the same thing as 1.48 meters. And we know the length of the tree's shadow was 648 centimeters, or 6.48 meters. I asked my daughter what her height was, and we actually went ahead and verified it just to make sure we'd had some accurate numbers. And she is 175 centimeters tall, or 1.75 meters. So now we have three of the values that we need, leaving us just one unknown. So now we can substitute them into our proportions and solve. So I'm going to use the ratio. The ratio is comparing heights to shadows. Okay. And so using the values that I don't know the height of the tree, but I do know my daughter's height was 1.75 meters. And the length of the tree shadow was 6.48 meters compared to my daughter's shadow, which had a length of 1.48 meters. We need to isolate our height. And so we can see that we need to multiply both sides by 6.48. to cancel off that denominator. So our height is going to be 1.75. Oh, my little solar is not working. Okay. 1.75 divided by 1.48 times 6.48 giving us a height of about 7.66 meters. So what does that mean in terms of feet? Well, we know that 1 meter is about 3.28 feet. Okay. And so we can use this conversion ratio, saying that we have 7.66 meters, multiply that by 3.28 feet for each meter. My meters will cancel off, and so I can see that my height is going to be 7.66 times 3.28, or about 25.12 feet. Does that make sense that the orange tree is over 25 feet tall? Well, we have our second strategy using the clinometer to help us confirm this measure, but I think I'd like to go outside and just kind of estimate. And because if you saw when we first started looking at the orange tree, you may have noticed that there was a shed by the tree. And so looking at the shed, there's a door, and I know that the standard height of a door is about 80 inches. And so I want to go outside and see about how many of those door heights would it take to get up to the top of the tree. So hang on, and I'm going to go check. Okay, so I went outside and using my little fingers to try to see how many of those doors could fit from the ground to the top of the tree. I noticed that it took about 3.5 doors to the top of the tree. And remember, we said that each door had a height of about 80 inches, which, dividing that by 12, is about 6 2/3 feet. So 3.5 doors times 6.67 feet gives me about 23.35 feet. So, using heights and shadows, I can see that that height of that tree is about 25 feet. Estimating just by sight, I get about 23 feet, so fairly close. Still slightly off by a couple of feet. Makes me wonder how accurate our measurements were. If you recall, there was a point when Morgan and I were measuring the shadow of the orange tree, and we were debating on where the shadow ended, and we decided at 648 centimeters, but now I'm wondering if maybe we should go back. Well, we can't go back now because the sun has changed its location, but in the future, it makes me wonder if it would have been better to take multiple measures and maybe gotten an average to make sure that we were getting some accurate data. But we have some measures from our first strategy. Let's take a look at finding the height of that highest orange using our second strategy, the clinometer.
Okay, so for our second strategy, we don't need to wait for the sun to shine to have shadows. All we have to do is make a tool called a kilometer. A kilometer measures the angle of elevation. So if you think about what we mean by angle of elevation is if we are looking straight parallel with the ground, that's at 0 degrees, but as we look up, an angle is formed at the ground, and that's called the angle of elevation. And so the kilometer is going to help us measure that. So to create our own kilometer, we need a couple of things. First of all, you need a tool that measures angles, and so that would be our protractor. We need a piece of string, maybe about a foot long or so, just long enough that you could tie it to the protractor and tie a little weight to it. I'm using dental floss because it was easy to get, and most of us have it at home. You need to have some tape so that you can fasten the string to the protractor, as well as a straw. So I have a eco-friendly reusable straw, but you can use any straw as long as you can see through it, because this is what we're going to use to sight the top of the tree or that highest orange, or actually whatever orange you want to see how high it is above the ground. And then you need a small object. I just went in our garage and I grabbed a washer, but any kind of object that you could easily tie to the string so it weighs down. So we begin by grabbing the protractor, and in the center of the protractor you have a little hole. You could thread that string through the hole and tie it. Now if you have a protractor that doesn't have a hole, just use your tape and tape that string to the protractor. Okay. So let me tie it one more time, just to make sure it doesn't come off. Okay. And now I have my string tied to my protractor. The next thing we want to do is we want to weigh it down. So get that little object that you're going to use for your weight and just tie it to the other half of the string, or the other end of the string. Okay, so now I have my protractor with my weighted string. The next thing we want to do is we want to attach the straw to the protractor. Now, since we're measuring the angle of elevation, there's actually two ways that we can attach the straw to the protractor. So one of the more common ways that we see the straw attached is to tape it along the 180-degree mark of the protractor. Not the edge of the plastic, but the actual 180-degree mark. If you do that, you notice that if I hold my straw level, parallel with the ground, it actually measures 90 degrees. So you have to ask yourself, does that make sense that if I am looking straight across, parallel to the ground, does that make sense that I have an angle of elevation of 90 degrees? Well, hopefully you're saying to yourself that that doesn't make any sense. And so if we attach the straw this way, we have to actually find the complement of 9 degrees. In other words, if I slightly angle up my straw, you can see it's moved over 10 degrees. And so to read this measure, I would take 90 and subtract off the 80 because it's falling on the 80-degree mark. So 90 minus 80 gives me an angle of elevation of 10. And you can see as I continue to increase the angle of elevation, the degrees increase. So now it's lying at 60 degrees. 90 minus 60 means I have a 30-degree angle of elevation. Now, if I didn't want to have to find the complement, another way that you could attach the straw is to actually just attach it right there at the 9-degree mark. And that way you can see, as long as I've attached that, the end of the string is falling straight down on that 180-degree mark. Now it makes sense when I hold my straw level that my string is falling at the 0-degree mark. But notice that if I increase the angle of elevation, my string is no longer falling on my protractor. So if you use this method, you're going to have to look through the straw from a different direction. So now again, if I hold it level, and then I increase my angle of elevation, now the string is falling at 10 degrees, 20 degrees, and so on. So I personally like this method better. So I'm going to get some tape. And attach the straw at the 9-degree mark. It helps if you have clear Scotch tape so you can still read the numbers on the protractor. And now I have my beautiful clinometer ready to go. So in order to use this, all I have to do is look through the end of the straw until I can see the orange that I want to measure the height of, and then see where the string hits the protractor. Now it might be difficult to do by yourself because, you know, once you take it away from your eye, you may move the protractor. So I'm going to ask my daughter Morgan to come back and help me measure the angle. Okay, so I went to go get some additional tools because before we can measure the angle of inclination, I need to measure the distance between me and the orange, the horizontal distance between me and the orange. So I have some tape so I can mark off a point where I'm standing and the horizontal distance between me and the orange. And then I have my tape measure so I can measure those distances. So I'm going to start by measuring my location, marking my location, and then I'm going to go see if I can get underneath that highest orange and mark its location. Hey, you want to come and hold down this tape measure for me? Mm-hmm.
How far is the tape measure?
760 centimeters. Ready?
I bet she dies because
So this is 748. Okay, now that I have the distance between, the horizontal distance between me and the orange, now I just need to find it in my clinometer. Okay, can you measure that angle? Mm-hmm. 11 degrees. 11 degrees. Okay, so we have the measurements for our highest orange. Let's take this opportunity to verify our findings by measuring the height of a second orange. We can use the kilometer to determine the height of an orange that's closer to the ground that we could actually measure. So what we're going to do is we're going to measure the horizontal distance from where I'm standing to where that orange is located, and use those measures and the angle of inclination to calculate the height of that orange. And then later, we're going to go back and actually use a tape measure and measure how high that orange is off the ground to see how precise this method is. It's just a good opportunity to make sure the strategies that we're trying really work. So, I already have my location marked. I'm going to go stand underneath that second orange, mark its distance, and then Morgan's going to help me measure that distance out.
Wait, so you're in line with your point.
Okay, so the first measure was 760 centimeters. The second one is 720. So now all I need is my angle of inclination. Make sure my tool's going to work. Okay, can you measure that angle? Mm-hmm.
It's in between 2 and 3. So 2.5?
Okay, let's go at 2.5 degrees. So we have our distance, we have an angle. Let's go do some calculations.
Okay, let's look at our second strategy of using a clinometer. So if you recall, we had our orange tree, and there's a little orange near the top of the tree that we wanted to see how high off the ground that orange was. And so we stood a distance away from the tree and looked at the orange through our the straw on our clinometer, creating that line of sight. And this allowed us to determine the angle of elevation. So to see the angle of elevation, you can see if we're standing on the ground and we draw a line parallel with the ground, now you can see my angle of elevation right here. Here's my angle. And it turns out that we have a situation with a right triangle, very similar to strategy 1, where we had 2 right triangles. In this case, we only have 1 right triangle, and so I can go ahead and draw a line perpendicular to the ground, so you can see that I now have a triangle. And how do I know that this triangle is a right triangle? Well, remember, we drew this line parallel to the ground, and so we have parallel lines cut by a transversal, so we see that corresponding angles are the same. And so now we have a right triangle, and we can see that in order to figure out how high this orange is, we actually need to calculate 2 different heights. First of all, the height of my right triangle, and then secondly, this distance here. And you may be wondering, what is this distance from the base of the tree to the base of the right triangle? Well, if you look across, this actually is the height of my eyes. So this distance here is the second height that we have to find. And so our goal is to find the height of this orange by using two unknown heights and the distance that that orange was, the horizontal distance that orange was from the tree. And you can see that distance from me to the tree is the same as the length of this side of my right triangle. So we don't have two triangles, two similar triangles. And so how are we going to figure out these two heights? Well, this height I can just measure. But in order to figure out this height, we need to use a new tool. And that tool is called trigonometry. So our strategy is actually using a kilometer and trigonometry. Trigonometry comes from the Greek word trigon, which means triangle, and metry, which means measure. And so we're going to use the measures of a triangle. And if you recall, every triangle has angles we can measure and side lengths we can measure. And so it turns out that there are what we call trig functions that we can use. We can input an angle measure, and it will give us a ratio of side lengths. And so there are 6 trig functions that are based on a right triangle. So let me scoot this over a little bit so you can see, well, maybe I could fit it in right here. Okay, so if we have a right triangle and an angle, okay, so there is the right angle, and then there are 2 acute angles. So just using one angle as our reference angle, we need to be able to refer to the different sides of the triangle. Well, so looking at these sides and relating them to our angle, we all know that every right triangle has a hypotenuse. Remember, the hypotenuse is the longest side, and it is directly opposite the right angle. And then we have a side that is directly opposite the angle, and that's referred to as the opposite side. And then the last side, this is the opposite side, and then the last side, which is right next to or adjacent to the angle, is referred to as the adjacent side. And so, having our angle and knowing how to refer to the sides of the triangle that relate to that angle, we can use one of 6 basic trig functions to figure out missing side lengths. So I went ahead and wrote these up just to save time. So we have 6 basic trig functions: sine, cosine, tangent, and then the reciprocal of each of those, the cosecant, which is the reciprocal of the sine function, secant, which is the reciprocal of the cosine function, and cotangent, which is reciprocal of the tangent function. And so the sine function works. Remember, every function has an input and an output. So if we input an angle measure, the output will be a ratio of the side lengths of the opposite side over the hypotenuse. Same thing with the cosine. If I input an angle measure, the output would be the ratio of the length of the adjacent side over the length of the hypotenuse. And same thing with the tangent. Input the angle measure, and it will output the ratio of the length of the opposite side over the length of the adjacent side. So, looking at our situation, which trig function would we want to use to determine this unknown length? Well, we know how far I was standing from the tree, and we need to determine this height. So it looks like from our angle of inclination, we're looking for a relationship using the opposite side and the adjacent side. Which function is a ratio of the opposite side to the adjacent side? The tangent function. So, in order to start figuring out the height of that orange, we need to find the tangent of our angle of inclination. And if you recall, the angle measure was 11 degrees. And so we find the tangent of that angle, it's going to be equal to the ratio of the height of my right triangle, which I don't know, to that horizontal distance from where I was standing, which was 760 centimeters plus 748 centimeters. We changed those to meters, so 7.6 meters plus 7.48 meters gives us a length of 15.08 meters. Okay. So actually, let me go ahead and label our diagram with those measures. It was 11 degrees. And by the way, since I'm labeling our diagram, the height from the ground to my eyes was 1.66 meters, 166 centimeters. Okay, so let's calculate the height of the right triangle. And so to do that, you can see that we need to isolate that height by multiplying both sides by 15 and 800ths. So our height is equal to 1508 times the tangent of 11 degrees. And so we can just input that into our calculator. If you want to make sure that you have a scientific calculator and that the setting of that calculator is on degrees. So looking at my calculator, see that little tiny D? I don't know if you could see that on my calculator. That tells me I'm in degrees. So I just need to enter in 15.08 tangent 11 degrees times the tangent of 11 degrees equals about 2.93. So we have a height of about 2.93. Okay, so now recall that this height of 2.93 meters only represents the height of my right triangle. In order to find the height of the orange, I'm going to have to combine the height of the right triangle with the height of my eyes above ground. So let me slide this up to make sure you can see what I'm writing. And so we know that the height of the right triangle was 2.93, and the height of my eyes above the ground was 1.66 meters. Adding those together, we get 4.59 meters. And so the question is, how many feet is that? So if you recall, 1 meter is equal to about 3.28 feet. So we're going to use this conversion factor. And so we have 4.59 meters times 3.28 feet for every meter. So I can get my meters to cancel out. So again, getting my calculator, 4.59 times 3.28 gives us about 15.06 feet. So the height of the highest orange is 15.06 feet. That's quite different than the height of the tree, because we thought that that highest orange was pretty close to the top of the tree. And using our first strategy of height and shadows, this is quite different. And so, if you recall, we thought since we were out there, we might as well take some other measurements. And so let's take a look at the height of that second orange and compare it to this height and see, is there something going on with this strategy or the other strategy? What's wrong with our measures? So let's take a look at that second orange. All right, let's calculate the height of that second orange. So all I really need to know is a little bit of information about my right triangle. So you know that we had an angle of inclination. Remember, Morgan had trouble determining whether if it was between 2 or 3 degrees. So we said, let's go with 2.5 degrees as our angle of inclination. We're trying to figure out that unknown height. And we know the distance from me and that tree was 760 centimeters or 7.6 meters. Combined with 720 centimeters or 7.2 meters. So 7.6 plus 7.2 gives us a length of 14.8 meters. So we still have that relationship to our angle. We have the opposite over the adjacent. So using the tangent function, the tangent of our angle, which is 2.5 degrees, is going to be equal to the ratio of the length of the opposite leg, which was our height of our right triangle, to the length of the adjacent leg, which was the distance away that I was standing. So just like in our previous problem, we're going to multiply both sides by 14.8 to isolate the height that we're looking for. And so we can see that the height is going to be equal to 14.8 times the tangent of 2.5 degrees. Oops, 2.5 degrees. So, putting that in our calculator, we have a height of 14.8 times the tangent of 2.5 degrees is equal to about 0.65 meters. 0.65 meters. But remember, we want the height of the orange tree, because remember, this was part of the tree. And so we need to add to that the height, right, from my eyes to the ground. And so that was, if you recall, 1.66. So the total height of that orange is going to be this 65/100ths of a meter plus the height of my eyes from the ground, which was 1.66. So adding those two together, the height of this orange, 0.65 plus 1.66 is about 2.31 meters. And again, using our conversion factor, we know that 2.31 meters times 3.28 feet per meter will allow us to convert 2.31 to feet, and we get a height of about 7.58 feet. How does that compare to the height of the tallest orange? Well, we said that this second orange was about halfway up the tree, and 7.58 does seem to be about half of 15 feet, so that seems pretty accurate. But if you recall, we chose an orange that we could actually measure the height of. So the actual height of that orange was 237 centimeters from the ground. And converting that to feet, right, so 2.37 meters times 3.28 feet per meter gives us 2.37 times 3.28, drum roll, about 7.77 feet. Pretty good, pretty good. So it looks like our strategy of using the clinometer with a little bit of trig gave us some measurements that actually make sense, but the strategy of using height and shadows gave us a height that didn't quite make sense. So think about what we learned today. We saw two different strategies, one using heights and shadows, right, and proportional reasoning, and the other also building on right triangles, but using right triangle trigonometry to figure out the unknown height. Both strategies ended up giving us two different answers. So what does that mean? What did we learn by using these two different strategies to find the height of these oranges? Well, there's one thing that we want to keep in mind whenever we are modeling with mathematics, and that's what this is using the mathematics we know to make sense of the world around us. That modeling with mathematics is always messy because it's based on different assumptions that we make and data that we collect. So when you think about it, with strategy one, we're looking for the shadow of that highest branch. So how does that highest branch relate to the orange that we found the height of in strategy two? I said earlier that it looked like it was about a foot below, but maybe my perspective was off and it was quite lower. Also, if you recall, we assumed that we were measuring the correct shadow in strategy one. Maybe we made a mistake and didn't quite get the accurate edge. And you notice that there was a taller tree behind the orange tree, and so maybe that affected that distance. So, the thing with data, it's only as accurate as the tools that we use and how we use those tools. So if you're going to try these strategies, keep a couple of things in mind. Could we have been a little bit more precise? Could we have been off with those distances we measured? Could a difference of a centimeter or two affect the findings that much? Same thing with the clinometer. We measured this angle and we had a little bit of difficulty getting a precise measure. How much difference would a degree make? And would it have made sense to have done multiple measures of these distances across the lawn, and then and maybe have done the average, maybe calculated a bunch of these at different times of the day, because the shadow lengths are going to be different, and found the average. And same thing here. Maybe we sighted that object from different locations. So there's lots of different approaches that we could have taken. I hope you take on the challenge of calculating the heights of tall objects around your home. Think about what tools you're going to need and how you're going to make sure that your results are accurate. Either way, have fun doing mathematics.